All right, everybody, what we're going to be looking at in this lesson is how we're going to do some basic operations with matrices. So there's a few basic operations that we're ultimately going to wind up doing. You know, how do you add or subtract matrices? How do you multiply a value to a matrix? It's kind of like how I would, not multiply two matrices together, but how could I multiply a single value to a matrix, kind of like a dilation in geometry. And how could I actually multiply a couple of matrices together? Uh, so each operation has its own unique procedures to them. And in order for us to get to that point of being able to understand, well, I have to do this to do this particular operation, we have to understand a little bit about, uh, matrices themselves as far as, you know, certain matrices you can do operations with and certain matrices you can't because they have to have, something similar to each other. They have to have the same size or the same number of rows and columns or some combination. And it's a little different depending on the operation that you're trying to do. So looking here, obviously this is just a reminder what you're seeing here about how an entry of a matrix is located. So here we're working with an imaginary matrix A. So because we called the matrix A, we use a lowercase letter a to represent an element of that matrix. And of course the I, that tells you what row your element of the matrix is in, and the J tells you the column that the element of the matrix is in. So let's say, for instance, I had A47. That would say I'm looking at something in row 4, column 7 of a matrix. Now, we're not going to look at anything nearly that big, but that's just, how things are located inside of a matrix. Now, the next thing that we're looking at here, the first thing that we want to be able to identify about two matrices before I can do basic operations with them is I have to be able to identify if a matrix is equal to another matrix, meaning are they the same size? Or, well, let me backtrack a little bit. In order for me to show if a matrix is equal to another matrix, just like anything else that says something is equal to something else, they literally have to be the exact same thing. So obviously they have to be the same size, and every entry in one matrix has to correspond exactly to the same entry in the next matrix. So what we're seeing here in the statement at the bottom that says matrix A being equal to matrix B will work if every element of matrix A matches correspondingly to the same element in matrix B, meaning that if A of 3, 2 was equal to a 5, then B of 3, 2 better equal to 5 also. That's kind of what that statement is saying, is that every element of matrix A and its corresponding element of matrix B has to be the same number. That's how we're going to be determining whether a matrix is the same or not. So here we have an example where we're asked, out of the two matrices that we see in the screen, are they the same? Are they equal to each other? So let's, just for the sake of keeping things consistent, let's call this matrix A, and let's call this matrix B. Is matrix A equal to matrix B? Now, looking at the numbers of matrix A, I have a 3, a 2, a 1, and a negative 2. And looking at the numbers of matrix B, I have a 3, a 1, a 2, and a negative 2. All of the elements of matrix A and all of the elements of matrix B are shared, meaning every number that I have in the first matrix and every number that I have in the second matrix are the same. So the values from one matrix to another are the same. But are they equal to each other? Now what we saw on the previous screen, let's just look at the very first one. A 1, 1, meaning what's in row 1, column 1? Well, in row 1, column 1 of matrix A, I have a 3. So looking at the exact same element of matrix B, row 1, column 1, in here I have a 1. Since the first element, since the element in row 1, column 1 of matrix A is not the same number that is in the same place of matrix B, we would say, no, these are not equal to each other because the elements from one matrix to another don't match up. Okay, so they're not going to be equal to each other. Even though they have the same numbers, because they're not in the same exact place from matrix to matrix, we would say no, matrix A is not equal to matrix B. Okay, so here is another example of looking at two matrices and saying, are they equal to each other? So let's go ahead and, again, for the sake of consistency, let's call the one on the left A, and let's call the one on the right B. So here we're saying, do the two matrices, are they equal to each other? Now here what we're giving an option for, it says if it's false or conditional, explain why. All right, so what does conditional mean? Well, let's take a look here. Looking at the first row of matrix A, I got a 1, a -3, and a +3. And in the exact same order of matrix B, I have the same numbers. All right, now in matrix A in row 3, I got a -6, a 3, and a -2, and I have the exact same values in row 3 of matrix B. Now when we look at the second row, we have a 2, a 5, and then a 1 in matrix A, and then a 2, a 5, and then an A plus a B in matrix B. So are they the same? Well, they're almost the same as it is. Every element of matrix A corresponds to the same number in matrix B. But there's just that one little hiccup. This one here in row 2, column 3, and this one here in row 2, column 3 are not the same thing. But because A and B, A plus B isn't actually a number. It's not like a 5 or a -8 or something like that. Because it's a different, it's just a variable. Well, maybe whatever A is and whatever B is, when I add them together, maybe that gives me a 1. So here I could say this is conditionally true. If A plus B actually equals 1. So if A plus B does equal 1, then yes, a matrix A and matrix B would be equal to each other. If A plus B, however, did not equal 1, then no. Obviously, that one element not matching up would say that the matrices are not equal to each other. So that's why we say it's conditionally true. It could be true if A plus B is equal to 1, but it could also be false if A plus B is anything other than 1. So that's what we're looking at there. Conditionally true because of that one tiny little hiccup. All right. So here what we're looking at, okay, final true, false kind of thing here. Say, okay, and again, let's kind of keep it consistent. We'll say this is matrix A and matrix B. So is matrix A equal to matrix B? Well, in this case, matrix A is a 3 by 2 matrix. And matrix B is a 2 by 3 matrix. Now again, they're trying to see, are you paying attention to a couple of things? Because the values, the numbers that are in matrix A and the numbers that are in matrix B, they use the exact same numbers almost in the exact same order. All right, but we're looking at the 5, the 4, and the 5 in matrix A, well, that makes a column, and the 5, the 4, and the 5 in matrix B, that makes a row. So some of the elements are going to match, but not all of them, because of that fact that they're the same numbers but in a different order. And here, looking at the size, here I have a 3 by 2 matrix and a 2 by 3 matrix. So not only would matrix A not be equal to matrix B because the elements don't match up, but we could also say that A is not equal to B if they're not even the same size. There's no way that they can be considered the same matrix. So even though they have the same numbers, they're not in the same order, meaning the elements don't really match up. Because if I look at row 1 or row 2 column 1 of matrix A, I have a 4, but if I look at row 2 column 1 of matrix B, I have a 1. So the elements don't match up, but they're not even the same size. So because they're not the same size, they definitely cannot be equal to each other. So in order for us, the reason why we want to be able to identify if matrices particularly are the same size is because we're going to be looking to see, well, can we add or subtract matrices? And that's exactly what we're seeing here. If I want to add or subtract matrices, they have to be the same size. So if matrix A is a 2 by 2 and matrix B is a 3 by 3, if they're not the same size, you can't add them together. And so let's say we can add them. Let's say matrix A and matrix B are both the same size. Well, in order to add them together, we add the corresponding elements together, meaning row 1, column 1 of matrix A gets added to row 1, column 1 of matrix B, and so on. Okay? So that's kind of what that stuff here at the bottom of the screen is kind of telling you. Whether I'm adding or subtracting, we're going to kind of combine the same elements together. Now, the fact that this is a C and this is a D makes that's arbitrary. It's not saying that if I add something I have to call it C, or if I subtract something I have to call it D. Don't let the fact that they're using different letters for the different operations throw you off. That doesn't really matter. It just says I'm going to take the elements of A and B, and when I do, I'm going to call that matrix C. And in another operation, I'm going to take matrix A and B and I'm going to subtract them, and when I'm done, I'm going to call it matrix D. It's just an arbitrary choice. I could have called it matrix F if I wanted to. It makes no difference. So here, now this is, you might want to take a moment and pause the video at some point to write all three of these matrices down in your notes, so that way you could kind of use them for comparison later on. But we have these three matrices here, A, B, and C, and just to be clear, these don't necessarily produce the other one, because like the screen a second ago, it said if I say matrix A plus matrix B, I'm going to call that matrix C. Well, that's not what we're seeing here. The matrix that we call C on this screen is not the sum of matrix A and matrix B. It's like I said, the letter is just kind of an arbitrary choice. So here what we're going to do is we're going to say matrix A plus matrix C. Well, matrix A, well, let's just go ahead and while we have them here, since everything's kind of up at the top, matrix A, what is its size? Well, it has 2 rows and 3 columns, so this is a 2 by 3 matrix. Same thing with B. It has 2 rows and 3 columns, so this is a 2 by 3 matrix. And matrix C it has 2 rows, but it has 4 columns, so this is a 2 by 4 matrix. So what the first operation is asking us to do, to say matrix A plus matrix C, what would the sum be? Well, unfortunately, for A, meaning question A, here we can't actually add these together. because they're different sizes, we can't add them together unless the matrices are the same size. You can't add them together because when we add matrices together, we have to add all of the corresponding elements of one matrix to another. And matrix C has more elements than matrix A does, so there's nothing that I can combine them with. So because they're not the same size, we can't add them together. So these can't be added because they're not the same size. So sorry, matrix A plus matrix C, that doesn't happen. All right, so let's look at question choice B here, where we're saying matrix B minus matrix A. So matrix B minus matrix A, they're both 2 by 3 matrices, so that means we can go ahead and subtract those from each other. So I'm going to write them in the order that they're presented to us. So I'm just go ahead and write matrix B real quick. So 5, 2, 1, and 3, 4, and -5. So there's matrix A. I'm sorry, matrix B. Now I'm going to write matrix A real quick. So I have a 3, a 7, and a -2, 4, -5, and 11. So the way that we're going to look at these, and it might help if I pick a different color here. So the same elements have to be combined. Now, depending on how much you need to see as far as work is concerned, this is where you may need to say, oh, well, pause it or write down a question and say, and remind myself, ask Mr. Pierce, I need to see a little bit more detail here. But to try and save a little bit of space, okay, this 5, because it is in, row 1, column 1, and this 3 is also in row 1, column 1, those are the two elements that correspond together from one matrix to the other, and so those are what we are going to subtract from each other. So here, my matrix should be the same size for my solution as what I started with. They should be a 2 by 3 matrix because since the matrices have to be the same size when I add or subtract them, the answer has to be the same size as well. It's just the numbers change. So we're going to say 5 minus that 3. That gives me a 2 here. Okay, so I don't know. I don't think I need to necessarily pick a different color each time, but let's go ahead and keep it consistent for the time being. Now I'm going to take that 2 that is in the second column of row 1 and the 7 here that's in the second column of matrix A, and we're going to combine those together. So I'm going to say the 2 minus the 7 that's there. So 2 minus 7 is going to give me a -5 for the second element of row 1 of my answer. All right, so now let's pick a slightly different color here. Let's go, I think we can see that one okay. So the last element of the first row and the last element of the first row here, and we're going to combine those together. So +1 minus a -2. Well, +1 minus a -2 is a +3 here. All right, and that's essentially how we're going to kind of combine the elements of one matrix to another one when we're adding or subtracting them. The corresponding parts of one combined to the corresponding part of the other one through whether we add or subtract them. So let's finish it off. I think we can do away with the color coding now, but if you need, again, a little bit more detail here, let me know. So 3 minus the 4 of the bottom rows, well, 3 minus 4 is a -1 here. And moving on, 4 minus a -5 gives me a 9 for the next element. And 5 minus 11 will give me a -16 for my final element. So here, this is what B minus A is equal to. So there is the solution to that example. So now let's look at the last one. Now, if we could subtract the two matrices from each other, we can definitely add them as well. So matrix A plus matrix B, and again, I'm going to just go ahead and kind of write them down just because I think it's a good practice to have the matrix right there where you're needing it. Now, again, if you've already written it down and you don't want to write it down again, that's fine. These are your own notes to use as you need. So 5, 2, and 1, and then the 3, the 4, and the -5. Oops, I'm writing this in the wrong order. Let me fix that. Oop, come here, give me a bigger eraser. Writing that in the wrong order. I'm writing matrix B again. We have to do it the order that they gave us. So they said A plus B. So A plus B is going to be the 3, the 7, and the -2 for that row, the 4, the -5, and the 11 for that row. And then we'll say plus. And so the next matrix, that's where I'm going to say the 5, the 2, and the 1, and then the 3, the 4, and the -5. So again, you know, at this point, probably we have the hang of it, but maybe we don't. And if not, I'm going to go ahead and color code these again, at least to start. Because they're the same size, we can add them together. And again, the same corresponding element of one matrix and the other matrix, that's what we wind up combining together. So again, the answer, A plus B, whatever we have, it's going to be a 2 by 3 matrix because that's what A and B are. The answer of a sum of the matrices has to be the same size as its individual parts. So the 3 plus a 5 will give me an 8. All right, and let's pick another color here. What did we do? Green last time, so let's do the same thing. The 7 here and this 2 here, those are going to combine together. And so 7 plus a 2, that'll give me my 9 for my next element of the first row. And again, this will be kind of the last color-coded thing that I do. I'm just trying to illustrate identifying the corresponding parts of the matrices as you do your addition and so on. But so here, the -2 and plus a 1, well, -2 plus 1, that is going to be a -1. So that's how we generate the first row of our solution, of our sum. So now let's speed things up just a little bit again. So now let's find the corresponding parts of the bottom rows. Well, the 4 and the 3, those correspond. So 4 plus 3 gives me a 7 here. -5 plus the 4 of the second matrix. Well, -5 plus 4, that's a -1. And then the last row, the last element in the matrix, 11 plus a -5, that's going to give me a +6. And there is the sum of matrix A plus matrix B. So first, in order to be able to add matrices together, got to be the same size. And if we're going to add matrices together that are the same size, we have to have the same corresponding parts. So here's the same screen again, just in case you need a little more space. But I didn't need more space, so we're going to move on. Now, here, this is not really something that you need. I'm not going to ask you questions about this. This is here strictly for explanation purposes. What you're seeing is something that goes way back to Algebra 1, maybe even a little earlier when you started talking about your order of operations. There are things known as properties of addition and multiplication, the associative property, the commutative property, the the distributive property. Okay, well, here what we're seeing is an example of how if I group things together differently, how does it affect the answer? And when I am grouping things differently, that's known as the associative property of addition. So here, like in the second row here, I'm putting A plus B in parentheses, and then I'm going to add C, but it's equal to, on the right side, the B and the C are in parentheses, and we're going to add, whatever that was. So let's just pretend that these aren't matrices for a second. Let's just say that this is 1, this is 2, and this is 3. And this is 1, and this is 2, and this is 3, because they're the same numbers. Well, on the left side, I'm going to say 1 plus 2, which will give me a 3. And I'm going to add the other 3 to it, which gives me a 6. Well, on the right side, the order of operations will say do this stuff in the parentheses. Well, the 2 and the 3 gives me a 5, and then I add the other 1, and I still get a 6. The associative property of addition doesn't change the answer if I change the way that they're grouped. And that's what this is telling you. So, excuse me, even with basic algebra, the way that I group things when I add them together really doesn't matter. And it's going to apply the same way with matrices. And that's really all this is kind of showing you. So you don't need to write that down, but since it's there, I wanted to explain it. Now we're moving on to multiplication. Okay? Now multiplication is where things are going to start getting a little different. Okay? And I think we're probably going to stop here with what is known as scalar multiplication. Now, scalar multiplication, at the beginning of the presentation, I said, well, what we're going to be doing is we're going to do something that I would attribute to a similarity, something that's similar to that you've done in the past is dilating something in geometry. Where you take some number and you multiply it by a scale factor to make it either bigger or smaller. You take the same number and you multiply it to a whole figure. Well, this is the same idea. Scalar multiplication says we're going to take a matrix, whatever the matrix is, and we're going to multiply every element of that matrix by the same number. Just like we would multiply all of the coordinates of something on a grid to make it bigger or smaller. That's why I say it's kind of like dilating something in geometry. So in the example that you see here where it says K times matrix A is equal to, and it has the matrix symbol, those brackets, and we're saying the K times the element A. And that's exactly what we do. We're whatever K is, whatever that number is, I'm going to multiply it to every single number that's inside of matrix A, however many there are. Okay, that's what scalar multiplication is. So here we have two matrices. We have matrix A, matrix B. They're the same size. They're both 3 by 2 matrices. So if we wanted to add them together, we could, but that's not what we're asked to do. Here, what we're asked to do is says, okay, well, can you do this scalar operation? Which, sure, no problem. Now, what this is telling us to do is says take 1/2 and multiply it to matrix A. All right, so what that is telling me to do is I'm going to say 1/2, and I'm going to just go ahead and write matrix A here, which is 6, 2, 3, -2, 4, and 8. And what I'm going to do is I'm going to multiply that 1/2 to every number that's inside of the matrix. So it's almost like distribution. The 1/2 times the 6, that gives me a 3. Half of 2 gives me a 1. So there's my first row of my product after I do the scalar multiplication. So 1/2 times 3 is 3 over 2, or 1.5 if you want to write it as a decimal. So the 1/2 times -2, that's a -1 here. So there's the second row. And finally, the 1/2 and the 4 gives me a 2, and 1/2 of 8 gives me a 4 here. So here is the product of my scalar multiplication where I said the constant 1/2 multiplied to all of the elements of matrix A, that's what we wound up getting. Now, the next example is going to combine a couple of things. All right. Now, we've talked about addition and we've talked about subtraction, and now we're talking about scalar multiplication. So here, I just moved to a different screen, but these are the exact same examples that I had up a second ago. It's just a clean screen so I can do some more work now. Now, what this is going to tell you to do, this is, just like any other algebra problem that you've seen, we're saying 2 times matrix A minus 3 times matrix B. So we're going to combine scalar multiplication with matrix addition, or in this case, subtraction. So let's go ahead and see how this is going to work. So I'm going to say 2, and I'm going to write matrix A. So that's going to be 6, 2, 3, negative 2, 4, and 8. So there's matrix A. And I'm going to say minus 3 times matrix B. So I'm going to say minus the 3 times matrix B. So I'm going to go ahead and write that. So 5, negative 5, negative 3, positive 4, 2, and a 6. Okay? So just like distribution or multiplication in a normal order of operations algebra problem, I'm going to take the 2 that's being multiplied to matrix A and do that first. Then I'm going to take the 3 and it's multiplied to matrix B, and I'm going to do that. And when I'm done, I'm going to then combine the elements through subtraction. So let's go ahead and do that. So distribute or multiply, or however you want to think of it, take the 2, multiply it to everything inside of matrix A, and I'm going to get 12, 4, 6, negative 4, 8, and 16. Now here's where some of us are going to get a little confused. Well, if I distribute the negative in, do I make it positive in between? Or you can. My advice is to say, let's just keep the sign that we started with there. Let's just keep it through the negative. And let's just multiply everything in matrix B by a 3, because it'll work out all the same anyway. So if I say 3 times 5, I'm going to get 15, and then negative 15, and then negative 9, 12, 6, and 18 here. So now we're going to kind of combine these elements. And for the interest of space, I'm going to just write my answer to the right of this. So again, just in case anybody needs to see it one more time, let's kind of identify some of our color coding things here. So this 12 combines with this 15 here, the same elements from one to the other. So here I'm going to say 12 minus 15. 12 minus 15, that's a negative 3. So the first element of my final answer is a negative 3. And then we'll kind of do the same thing with the next one. Let's say the 4 here and the negative 15 here. All right. So here I'm going to say 4 minus a negative 15. Well, that's the same thing as saying 4 plus 15. So my next element of my final answer is a 19, and so on. So the next row is for skip the color coding now, in case you, again, if you need to, make a note to yourself and bring it to me in either class or tutoring, and I'll, walk you through it a little bit more. But now we're going to say 6 minus negative 9, and that'll give me a positive 15 for the first element of the second row. Negative 4 minus 12 will give me a negative 16 for the next element. And 8 minus 6 gives me a 2. And 16 minus 18 gives me a negative 2. So here is our final solution. Now, that's about as much as we're going to include in this presentation. The next thing that we're going to really get into is going to be multiplication of matrices, where I actually say matrix A times matrix B or something like that. But this by itself, I think, is enough information for one presentation. So again, if you have any questions about anything that you've seen in the video, make sure that you have them written down and bring them to me either in class or in tutoring, and I'll be happy to help you with whatever question that you had. Otherwise, guys, thanks for watching, and hope to see you in class soon. So take care.